Okay, so this evening we are going to be talking about Newton's laws of motion. Okay. The reason why Newton's laws of motion are very important is because they give us a connection, or they give us a bridge between what you have been looking at so far, because we've been looking at motion in terms of acceleration, in terms of velocity, in terms of displacement, and that stuff. That's what we have been looking at, how we describe movement of things. We describe the movement of an object in terms of the distance or displacement, in terms of the speed or velocity, and the acceleration. So what we're going to get when we start using Newton's laws of motion is we get a connection between this description which we have of movement in a straight line with the mass of the object. So we can now bring in the mass of the object, because our description of objects and how they move so far has not involved any mass. But the truth of the matter is that any object which is involved in motion or in movement actually has a reluctance to move or a reluctance to stop. Okay? So any object which moves, accelerates, or has got displacement, covers some particular distance at a certain amount of space, actually has got mass. And mass is an important part of describing the movement of objects. So it is this connection between the acceleration, or how fast the velocity of an object changes, to the mass of an object. That's what we get when we look at Newton's laws of motion. Are we clear? So this is what is at stake. We want to get a connection between the mass of an object and the acceleration. How does the mass affect the acceleration? What causes the acceleration of an object? Definitely it's not the mass, because an object which is at rest has got mass, but it has got no acceleration. Also, sometimes an object can move. If an object is moving with constant velocity, it has mass, okay, and that mass is not going to change. However, at that particular moment, if an object is at rest or an object is moving with constant velocity, the acceleration is equals to 0. So in each of these cases, while there is no acceleration, this particular object has got mass. It doesn't mean that the mass is not important. No, the mass is important, and the mass affects the acceleration, as we are going to see. So during the course of this lecture, we are going to look at a description of mass of an object in terms of the inertia or the resistance of an object to change in motion. We are also going to be introduced to the three Newton's laws of motion. The first law of motion, what it says, the second law of motion, and also the third law of motion. We are also going to be introduced to this relationship, F is equals to ma, and you will learn during the course of our lecture that in fact this F here, with this formula F, represents what is known as the resultant force. Now, force is a vector. So if you have a resultant force, it means that you need to add a bunch of forces together. So you need to add a number of forces, or you might have just one force present. So if you only have one force, then that force is what constitutes a resultant force. But if you've got more than one force, then you need to add up those forces in one way or another so that you get a resultant force. So in this formula right here, we would like to let you know that the F here, which is represented here, is not a single force, but it is a resultant force. And you get a resultant by adding vectors together. In this case, you'll be adding forces which are acting on an object together. So the force, or the resultant force, is equals to the mass, which is the mass of the object, multiplied by the acceleration. So this is the connection This is the connection between the mass of an object, the acceleration, and the resultant. So the connection is the resultant force. So if you multiply the mass of an object times the acceleration of that particular object, what you get is the resultant force which is causing that acceleration. This formula is a bit misleading. It looks like the acceleration causes the resultant force. It is the other way around. It is the resultant force which causes acceleration. So you only have acceleration if you have the resultant force. So as you're going to see, if there is no resultant force present, then you don't have any acceleration. Okay? Then the other thing which we're going to bring to your attention is the fact that as long as you have got mass and you live on this earth, there is a force which is constantly acting on you, and that is what is called the weight of a body. The weight of a body is a measure of how much the pull of gravity is, and the weight of any body, we get it by multiplying the mass of that body multiplied by something called acceleration due to gravity. So we're going to see how we come up with this value of acceleration due to gravity, which we have been using in our previous classes. So for us to have a very good appreciation of Newton's laws of motion, we need to be on the same page by what we mean by mass, by force, and of course acceleration. Of course, we have been talking about acceleration, so I'm sure people now have a very good idea of what we mean when you're talking about acceleration. Acceleration refers to how fast the velocity of a body is changing. So when the velocity of a body changes, whether that velocity is increasing or that velocity is reducing, that is what we refer to as acceleration. So we have talked about this acceleration extensively in our previous lectures. So today we're taking a step forward. So we want to introduce mass and how it connects to force. Now, we have also talked about mass previously when we were introducing our base quantities, and we said that the mass of an object is a measure of its inertia. Okay? Mass of an object is a measure of the inertia of that particular object. Inertia refers to the tendency of an object to remain at rest, or the tendency of an object to change, to continue moving with constant velocity. So this is basically what any object with mass does. The more mass an object has, the more likely that it will continue to remain at rest. Also, the more mass an object has, the more likely that it is going to be difficult to stop this object. And how do you stop an object? You stop an object by changing its velocity. But if an object has got a large value of mass, it will be difficult for you to change its velocity. So basically, objects with mass tend to continue moving with unchanged velocity or with constant velocity. So if it's easy to change the velocity of an object, then that particular object's mass is less. On the other hand, if it's easy for you to change the velocity of an object which is at rest, then that particular object has got less mass. If the mass increases, if the mass of a body increases, it becomes difficult for you to change the motion of an object. So this is what we refer to as mass. It is a measure of how difficult it is to change the velocity or the motion of an object which is at rest, or of an object which is moving with constant velocity. So that's what mass is when we are talking about in a physics class and we are talking about mass. Yeah, the problem is also if you send a message, say you can't hear me properly, I will not see the message, I will see it later on. So I don't know what the problem is, why you can't hear me properly. Is that the same problem other people are experiencing?
Yeah, I think it's just network.
Okay, because I'm at home, but the internet I have at home is quite good. So maybe it's just a network problem. Anyway, also, there's a recording being made, so this whole thing will be available to you shortly. Okay. So, mass, as we have seen earlier, is measured in kgs, and we know what a kg looks like. At least you have an idea what a kg looks like. The new guy here really is the force. Okay. Now, what we refer to as force, what does force do? Force changes the velocity of an object. That's what force is. Force changes the velocity of an object. So if there is a force present, that force tends to change the velocity of an object. So if the velocity of an object does not change, then you don't have a force. Okay. So force, of course, is a vector. It has got size. So the force has to point, needs to have a certain size, and also it needs to act in a particular direction. So that the direction of the force basically determines the direction in which the body is going to accelerate. So if the force is pointing in a particular direction, then the body tends to accelerate in that particular direction. When we say the body tends to accelerate in that particular direction, we simply mean that the velocity of that body will increase in the direction of the force. That's what we mean. Okay? And how do you get the force? Well, the units of force are newtons. And what does a 1 Newton force look like? A 1 Newton force is a resultant force which, when given to a 1 kg mass, causes an acceleration of 1 meter per second squared. So if you have a 1 kg mass, then a force of 1 Newton acts on this particular object. Then the velocity of that particular object, this 1 kg, will increase or will change by 1 meter per second every second. So at one point, if the velocity is 0, the next second the velocity will be 1, the other second the velocity will be 2, like that. So that's what we mean, and that's what force does. Okay? Force causes the velocity of an object to change. So that's how we are defining force. Any force will cause the velocity of an object to change. So what does Newton's first law of motion say? Well, Newton's first law of motion is primarily concerned with objects which are at rest or objects which are moving with constant velocity. An object which is at rest has got no acceleration. The velocity of that object does not change. An object which is in motion but it's moving with constant velocity also does not have any acceleration. So Newton's first law of motion is telling you what it is going to take for you to change the velocity of an object which is at rest or the velocity of an object which is moving with constant velocity. It says that the velocity will remain the same until it is acted upon by an external force. So if you want to change the velocity of an object which is at rest, or you want to change the velocity of an object which is moving with constant velocity, maybe you're driving a car. Your car is moving at 60 kilometers per hour, which is one of those speed limits you're allowed to drive a car with. So if you're driving your car at 60 kilometers per hour, then maybe you see an accident scene in front of you, or you see a policeman trying to stop you. Then you apply the brakes. Okay? So for your car to reduce in speed, you need to apply brakes. So when you are applying the brakes, you are applying an external force. So there's going to be an external force which is going to act on your car. This external force is going to result in your car slowing down. Or maybe you want to overtake some person who is driving slowly in front. So again, you press on your accelerator. That action of pressing on your accelerator is going to cause your engine to generate more force at that particular point. And this force is going to result in your velocity changing. So, what Newton's first law of motion says is that you need an external force for you to change the velocity of an object which is at rest, or for you to change the velocity of an object which is moving at constant velocity. So here, force is the changer of motion. So what we're basically saying here is that force, when a force is present, what we are saying is force. When force is present, that force is going to cause the velocity of the object to change. Either the object's velocity is going to increase, or the velocity of the object is going to reduce. Either way, whether the velocity increases or reduces, it doesn't matter. The point here is that the motion or the velocity of this object has changed, and for you to change this velocity, you need a force. Are we clear on what Newton's first law of motion says?
Yes, sir.
Okay. Next, we move on to Newton's second law of motion. Now, Newton's second law of motion gives us a relationship between this force, which is needed for you to produce acceleration. Okay? And the kind of force we are talking about here is not a single force. It is what is known as the resultant force, or the net force. That's what you're talking about. So what we are concerned about here, it's not a single force, but this thing called resultant force or net force. Resultant force or net force is a combination of forces. You need to add different types of forces. As we are going to show very, very soon, you will find that even an object which is very innocent has got a bunch of forces acting on it. Okay, so you need to add these forces. When you add these forces, then after you add them, if the result or if the sum of these forces is not equals to 0, then you have something called the resultant force. This resultant force can be positive, or this resultant force can be negative. But as long as a resultant force is present, that is good. Okay, so what Newton's second law of motion says is that if the resultant force F acting on an object of mass m is not 0, so if the resultant force is not 0, sometimes it can be 0, because when you add these forces acting on an object, sometimes they can give you a resultant force which is equal to 0. But we are being told that here that if the resultant force is not equal to 0, so what's going to happen if the resultant force is not equal to 0? It says the object accelerates in the direction of the force. So if the resultant force is present, that means that the resultant force is not equal to 0, then the object accelerates in the direction of the force. What this means is that the velocity of the object is going to increase or is going to decrease in the direction of the force. If the resultant force is positive, then the velocity of the object will increase in the direction of the force. If the resultant force is negative, then the velocity of the object will reduce. Okay. So, if the resultant force is present, the first thing is what will be the direction of the acceleration? In what direction is the object going to move? Here we are told that the object is going to move in the same direction as the force. Okay. The next thing is the size of the acceleration. That's the next thing, because acceleration is a vector. It has got size, it also has direction. So we know the direction of the acceleration. The acceleration depends on the force. Whatever the direction the force is pointing in, that is going to be the direction of the acceleration. So you should get it very, very clearly here that it is the resultant force which causes the acceleration. It determines, the resultant force determines the direction in which the body is going to accelerate. So if the resultant force is pointing in a particular direction, that is the same direction in which the body is going to go. So let's move on to the size. What is the size of the acceleration? The acceleration A is proportional to the force F. So the acceleration is proportional to the force. So if the resultant force is large, then the acceleration is also large and inversely proportional to the mass of the object. Inverse proportionality here with respect to the mass and acceleration means that if the mass of the object is large, it will be very difficult for you to change its velocity. On the other hand, if the mass of the object is small, it will be very difficult for you to change. It will be very easy for you to change the velocity of that particular object. That is why if a bunch of cars stop at the traffic lights, if cars stop at the traffic lights, you will notice that when cars start off, small cars like Vitz, Ranex, and all these small cars with small mass, they start off quickly. Their velocity changes very fast because they have got a smaller mass. The small mass makes sure that their velocity increases quickly. That is the inverse proportionality. However, if you have a truck which is carrying, let's say, dirt, that truck is heavy. So when it starts, it will start off slowly. That's the one thing which is going to happen. When it starts, it will start off slowly. However, you will also notice that the same small cars like Vitz and Ranex, Corollas, which start off quickly, you will find that most of these small cars have been bashed at the back. The reason why they've been bashed at the back is because these small cars, they can come to a stop very quickly because of their small size. So they can change their velocity very fast. So they can come to a stop within a short period of time. However, if this small car stops in front of a truck, that truck is heavy. The heaviness of the truck, according to Newton's second law of motion here, it says the acceleration is inversely proportional to the mass. Since the truck is heavy, it has got a large mass, that means that it is going to come to a stop very, very slowly. So usually you find an accident where a truck has hit into the back of a Vitz. The reason is very simple. It's because the driver of the Vitz does not understand Newton's second law of motion. Some of these drivers of these small cars, they don't understand Newton's second law of motion. You should not stop in front of a truck because that truck will not come to a stop the same way your car comes to a stop. Your car will come to a stop quickly, but the truck is going to struggle to come to a stop. That's what this means. When it comes to mass and acceleration. So the mass of an object determines how much the acceleration is going to be. How much the acceleration of that particular object is going to be. If the mass of the object is large, then the acceleration is going to be smaller. If the mass of the object is small, then the acceleration is going to be large. At the same time, as you can see, if the resultant force is large, then the acceleration is going to be large. So this A is equals to F divided by M. That's what Newton's second law of motion says. Newton's second law of motion says about the acceleration. But it's not very neat. So usually what we tend to do is we tend to rewrite it like this. We tend to rewrite it as F is equals to MA. So when you write it as F is equals to MA, your interest is in the acceleration. What does the acceleration depend on? The acceleration depends on the existence of a resultant force. You can have an object with mass, but this particular object is at rest, or this particular object is moving with constant velocity. If the object is at rest, the acceleration is equal to 0. If the object is moving with constant velocity, the acceleration is equal to 0. And if the object is at rest, or the object is moving with constant velocity, what that means is that this F is not present. So if the acceleration is equal to 0, it does not mean that the object suddenly has got 0 mass. No, the object still has mass. Okay? Whether the object is at rest or the object is moving with constant velocity, that object still has mass, and the mass of that object does not change. But if it is at rest, then the acceleration is equal to 0. Also, if it's moving with constant velocity, then the acceleration is equal to 0. So what that means really is that if the acceleration is equal to 0, it means that there is no resultant force present. Are we clear? That's why we said that the acceleration does not, you can have mass, but you're not experiencing any acceleration. The reason is very simple. It's because the acceleration depends on the existence of a resultant force. For you to have, for an object to have acceleration, it needs to experience a resultant force. So a resultant force needs to act on that particular object. Are we clear? Are we clear on this resultant business?
Yes. Yes, sir, we are clear.
Yes, so you need to have a resultant force. Yes, you might have a question on how do we get resultant force. We'll tackle that later on how do you get resultant force. Right now, the thing is, you need to understand that for acceleration to exist, you need to have resultant force. If resultant force is not there, if the resultant force F is equal to 0, you can have whatever mass you want. A small mass, a large mass, but as long as there is no resultant force, you will not have acceleration. Okay, so you need to have the resultant force for you to have acceleration. So it is a requirement that if you want the velocity of something to change, you need to have a resultant force. So usually we are interested in a couple of things. We are interested in the resultant force along the x direction. We are interested in the resultant force along the y direction. So what we do, if you're looking at an object, then you look at all the forces which are acting along the x direction. Which forces are acting along the x direction? You look at them, you identify them, then you add them together. Also here, we tend to look at the forces which are acting in the y direction. So either it's pointing up in the positive y direction or pointing in the negative y direction. Whichever direction it is, whether it's a force is pointing in the positive x direction, positive y or negative y direction, that is a force acting in the y direction. If the force is pointing along the positive x direction or the negative x direction, that is a force pointing along the x direction. So the x direction usually most of the time is the horizontal direction, and the y direction is the vertical direction. So once you identify those forces acting along the x direction, then you add them. That's what gives you this thing here. Then you add those forces. This is what gives you this funny thing here. This is the sum of the forces along the x direction. So when you add those forces, then you get this. This is what we call the resultant force. The resultant force along the x direction. So the resultant force, as you can see here, along the x direction is equals to the mass of the object multiplied by the acceleration of the object along the x direction. Why? It is because an object always accelerates in the direction of the force. So if you're talking about the resultant force along the x direction, like in this case, then the resulting acceleration will also be along the x direction. Are we clear? Also here, if you consider the resultant force along the y direction, so you identify which forces are acting in the positive direction, which ones are acting in the negative y direction, then you add them. Then you get a resultant force. That resultant force will cause an acceleration which is in the y direction. Are we clear? So this is the relationship. This is the relationship between resultant force and acceleration. Newton's second law of motion. You identify a bunch of forces acting along the x direction, you add them. Usually we tend to identify the direction in which the object is moving as the positive direction. So if along the x direction an object is moving in a particular direction, we tend to choose that as the positive direction. Okay. So, how would you find the acceleration from this formula here? For you to find the acceleration, you simply divide the resultant force along the x direction by the mass. When you have a value of resultant force, once you find the resultant force by adding the forces, then you divide that resultant force by the mass, you're going to get the acceleration along that particular direction. The same thing applies here. When you get the resultant force, when you obtain the resultant force acting along the y direction, then you divide that resultant force by the mass, it's going to give you the acceleration along the y direction. This AY and AX, as you can see, AY, that is the acceleration along the x direction, and AX, the acceleration along the y direction. These are components. This is how much is the acceleration along the x direction and how much is the acceleration along the y direction. Since AY and AX are components, you can find out how much A is by doing this. A is equal to the square root of AX squared plus AY squared. This is how you obtain the size of a vector if you know its components. So AX and AY, these are components of the resultant force, of the acceleration along these directions, AX and AY. So this is very, very important. Your forces which are acting on that particular object might not be pointing exactly along the x and along the y. But for each of that force, you need to find out what is the x component of this force, what is the y component of this force. So you do the vector thing. You create a table of forces. Then for each force, you find out what is the x component, what is the y component. For each force acting on this particular object, what is the x component, what is the y component. Then you add together the x components. When you add the x components, if you get a force which is not equals to 0, then you have a resultant force. That is your resultant force along the x direction, which is this guy. That is a resultant force along the x direction. When you add the y components of the forces, then you get this guy, which is the resultant force along the y direction. This resultant force along the x direction divided by the mass gives you the acceleration along the x direction. This resultant force along the y direction divided by the mass gives you the acceleration along the y direction. If you know the acceleration along the x direction and the acceleration along the y direction, then you can find out what the overall acceleration is, like this. Are we clear on Newton's second law of motion, what it talks about, and how do we use Newton's second law of motion to obtain our acceleration? Okay, next we move on to another law, which is called Newton's third law of motion. Now, Newton's third law of motion explains something which is very, very important. Newton's third law of motion can be used to explain why, as we are going to see, despite an object experiencing different types of forces, these objects sometimes they can tend to move with constant velocity, or in some other cases, an object can just remain at rest. The reason is as follows, according to Newton's third law of motion. For each force exerted on one body, so there is a force being exerted on one body, there is an equal but oppositely directed force on some other body interacting with it. This is often called the law of action and reaction. Notice that the action and reaction forces act on two different interacting bodies. So, if you exert a force, if an object exerts a force on another object, that object on which the force is being exerted will exert an equal but opposite force on the body interacting with it. This is what's known as the law of action and reaction. Equal but opposite reaction. Okay. Are we clear on this? This will become very evident as we talk about this other thing called the law of universal gravitation. Yes, there's a question?
Why is it considered equal?
Why is it considered equal?
Why is the force considered equal? Can you give an example? If I was to slap someone, the force that person would receive, or at least the force that person would feel, is just the same out. So how come it's considered equal?
No. You see, if you were to slap someone, okay? If you slap someone, it doesn't mean that you're not going to feel pain. You're also the person you're slapping will feel pain, yes, but you are also going to feel pain in your hand. So it's not as if you can go around slapping people without feeling pain. Are we clear? No, have you ever slapped someone without feeling pain in your hand?
No.
Yeah.
But the pain must be equal. I'm saying this point that says it's equal.
It's equal but opposite. Now, you see, it depends on what it is you're interacting with. For example, if you have I'm assuming you're seated on a chair right now, and maybe your computer is on a table, okay? You have got a force called weight acting on you. Are we clear? And maybe in that particular chair you're seated on, you're not the only person who sits on that chair. So right now, you are the one seated in that chair. So you are exerting a weight on that chair. So you are exerting a weight. The force you're exerting is the weight. So your weight is being exerted on the chair you're seated on. Okay? Now, that weight which is being exerted on you is supposed to increase your acceleration. But it doesn't. The reason why it doesn't is because the chair you're seated on feels your weight. Your chair is not happy with the fact that you're sitting on it. So your chair decides to push against your weight. So it tries to generate a force which is equal but opposite. This is what chairs and tables do, always. They try to generate a force which is equal and opposite. If a much bigger person comes and sits on that chair, that big person is going to exert a much greater force on that chair. So the chair is now going to sense, oh, the force which I'm feeling is much greater than the previous one. So it will try to generate an equal and opposite force. However, if we keep on increasing the size of people sitting in this chair, there is only a maximum limit where maximum amount of force a chair can generate in reaction. Okay? So if the chair is not able to generate that much force equal to the force being exerted on it, then that chair is going to break. Are we clear? When the chair breaks, then your velocity is going to increase. We say that you're going to accelerate. So you are going to fall to the ground. So always what happens is that if a force interacts with another object, that object will try to react. It will not be happy. It will try to react with an equal but opposite force. You have your desk. On that particular desk, you have put your computer, you have put your books. So that computer, that book, they are exerting a force on that desk. That desk is pushing back against. That's why those things are not falling. But if on that particular desk, then you decide to bring in a 25 kg of maize, you put on the desk, then you bring in another 25 kg of fertilizer, you put on that particular desk, that it's only a matter of time before that desk breaks. Are we clear?
Yes, ma'am.
So it doesn't mean that you can go on forever putting things on this desk. No. The way your desk is made can only allow only up to a certain maximum. Okay? Once it goes out beyond maximum, then your desk is going to break. Then these things on the desk are going to fall. So always, your chair, the floor, the rod, these cars passing on a road, when they're building a road, they dig under the road, they put gravel, they put stones, they put tarmac on top, different layers of tarmac. The reason why they're doing that is because they know some truck which is heavy is going to pass on that road. That truck is going to exert a force on the road. But what they want is for the road to push back against the truck. And that's how roads work, or that's how anything works. That's an application of Newton's third law of motion. Okay. So let's move on to something called the law of universal gravitation. Now, this law of universal gravitation basically says, in very, very simple terms, that any two objects which have got masses m1 and m2 are attracted to each other. Any two objects with mass are attracted to each other. Okay? The size of the attraction depends on how much mass these particular objects have. And the size of the attraction, Fg, that's what you call the law of force of gravity. The G is gravity. Force of gravity is equals to this G, the gravitational constant, multiplied by the mass of the object, the first mass, then the second mass, then divided by r squared, which is the separation between these two objects. Now, why is this important to us? Well, it is important because all of us and anything on the surface of the earth has got mass. Okay? But the earth is much larger than we are. So the earth has got a massive amount of mass. So you and me on this big planet, there's going to be an attraction. That's why people say everything which goes up must come down. Any particular small object is going to fall to the earth. There's going to be an attraction. You're always attracted to the earth. Okay, so what is the size of the attraction? Well, the size of the attraction depends on a couple of things. For example, it depends on the mass of the object on the surface of the earth. It also depends on the earth itself. And we measure the separation distance from the surface of the earth to the center of the earth. That's going to be the r. So in our case, when we are trying to work out the force of gravity, we let m1 be the mass of the earth. So let m1 be the mass of the earth, and the mass of the earth is this. Me is 5.97214 times 10 to the power 24 kgs. This is a big mass. Then we let m2 be the mass of any object on the surface of the earth, and we're going to denote that as m. So me is the mass of the earth, then m2 is the mass of an object on the surface of the earth, which we're going to denote as m. Then the separation between this particular object on the surface of the earth and the center of the earth, that is what you call r. So that is going to be the radius of the earth, and the radius of the earth is 6,371,000 meters. So with the mass of the earth, me, the mass of the object on the surface of the earth, and the radius of the earth, we can rewrite this equation number 4, we can relate it like this. So we write it as number 15, number 5 here. The force of gravity Fg is going to be equals to G, the mass of the object on the surface of the Earth, the mass of the Earth, and the radius of the Earth squared. This G is a constant. This is the value of G. 6.67 times 10 to the power minus 14. Now, the mass of the Earth is the same. The radius is the same. This G is the same. The only thing which is going to change is the mass of the object on the surface of the Earth. It can be you, it can be your book, it can be your phone, it can be your computer, it can be anything which is on the surface of the Earth. So the M is going to change, but these other things are not going to change. The G is the same. The G won't change depending on where you are. The mass of the Earth will remain the same. The radius of the Earth will remain the same. So we can get these constants, then we bunch them together like this. So Fg, which is the force of gravity, is equal to the mass of the Earth, the mass of the object, the surface of the Earth, then G, ME, then divided by RE squared. These are constants. We know their values, so we can substitute them, and we give them a letter G. So this time is constant on Earth, and we denote it as G. So small g is equal to capital G, the mass of the Earth, then the radius squared. If you substitute for G, capital G, then the mass of the Earth and the radius squared, like we have done here, we end up with 6.67 times 10 to the power minus 11. Then on top here, we have got 5.97214 times 10 to the power 24. Then you've got 6,371,000 squared. When you do this calculation, what you end up with is this. You end up with G approximately equals to 9.81 meters per second squared. This is what we have been using as the acceleration due to gravity. So we did not just choose, as physics people, we did not just suddenly decide to say, the acceleration due to gravity is going to be 9.8. No, acceleration due to gravity depends on the planet where you live. It also depends on the radius of that planet. And when in the case of Earth, this acceleration due to gravity comes out as 9.8 meters per second squared. So what this shows is that when you are on the surface of the Earth, you are going to experience an attraction, and the size of that attraction will be such that your velocity is going to increase by 9.8 meters per second every second as you move towards the surface of the Earth. And that's how things fall. They fall towards the center of the Earth. So this whole thing here, which we have there, we can replace it with G, and what we end up with is this. Fg is equals to the mass multiplied by the acceleration due to gravity, this mg. This mg is what is called the force of gravity. This is the force with which the Earth pulls on you. Are we clear? So as long as you've got mass, as long as anything has got mass, left to its own devices, that particular object, if it's not being stopped by anything, it will get pulled towards the center of the Earth.
Can I ask a question?
Yes.
Can we consider force of gravity to be an upward force or downward force?
Things fall downwards. Always. Force of gravity falls, it's towards the center of the Earth, towards the Earth. So it always points down. Are we clear?
Yes, sir, thank you.
Now, this force of gravity, when I say force of gravity, it might be maybe strange to some people, but this force of gravity is what is also known as the weight of an object. So what you might be familiar with is what is called weight. But most of us also tend to mistake weight for mass. Weight is not equal to the mass. Weight is a force with which the Earth pulls on any particular object on its surface. That is what is called weight. And the weight is the same as the force of gravity. Are we clear? The weight is the same as the force of gravity. Is there a question? I can't hear. Is there a question? So, as long as you've got mass, as long as an object has got mass, this particular object is being pulled by the earth downwards. The earth is doing a pull him down. Those of you who, I think if you have been to a bar, you have seen some people who are very, very drunk, they think they can sleep a bit for a second while holding their beer or holding a glass. The moment they try to sleep for a second, then they try to wake up, they find that their bottle or their glass is already on the ground. The reason is very simple. It's because if there is no other thing, okay, if there is no other force stopping things, those things will tend to fall. So your computer, you yourself, you've got mass, so you are being pulled. So if you're seated on a chair, then someone pulls that chair away under you, what is going to happen is that you're going to get pulled by the earth, you're going to fall to the ground. So actually, what you notice is that that chair you're seated on is actually pushing against you. It's actually pushing against the weight of you or the weight of that particular object. That is what is called Newton's third law of motion. Without the push of the desk or without the push of your chair you're seated on, you are going to accelerate by this much towards the earth. You're just basically going to fall. Is it clear? Are we clear?
Yes, sir. Yes, sir.
Okay, next we look at the types of forces. So the first type of force is what we have looked at, the weight. The weight is basically the force of gravity. The weight is the force of gravity with which the earth pulls on any particular object which is on its surface. And we know the weight with the force of gravity is equals to the mass times g. It always points down. That's the weight. That's the first type of force. So any particular object which has got mass, the first type of force which should come to your mind is the weight. The next type of force is something called the normal force. Now, the normal force is the force with which a surface which is experiencing a force, especially the weight, pushes back against the weight of that particular object. For example, the floor or the desk on which your computer is on or the chair on which you're seated. This desk or the chair feels the weight of that particular object on it. So what does it do? According to Newton's third law of motion, because the mass, like in this case, this mass is interacting with the floor. It's exerting a force, Fw, on the floor. The floor is not going to be happy about this. So the floor is going to push back with an opposite force, which is called Fn, the normal force. Equal but opposite force. Always. The floor or the desk will not overdo things. So as much as it can do more, it won't do that. It will exert an equal but opposite force. This equal but opposite force is always at 90 degrees to the surface. This Fn, the normal force, always perpendicular to the surface. So when you have a surface, if you have a surface, whether it's a flat surface or it is an inclined, it's a surface at an angle, the normal force which is going to be generated by that surface will always be at 90 degrees, perpendicular to the surface. Are we clear? So that is the second type of force. When you have an object with a mass, this particular object has got weight. If you get this object, as long as this object is not suspended in the air, it's not hanging in the air. If you get this object, you put it on a table, or you put it on the floor, or you yourself, you have got mass, which means you've got weight. You sit yourself in a chair. That particular chair will try to push against you. When the pushing against you is happening, the whole point of doing that is so that your velocity does not change. Your velocity remains the same, zero velocity, hopefully. Sometimes it can be a velocity which is not equals to zero, but it's not accelerating. For example, if you're in an elevator, okay, elevators tend to move with constant speed. They don't move like your cars where they're increasing in speed. No. An elevator is going to move up or down with constant speed. Okay. The other type of force is this force shown here, F. This force shown here, F, could be because maybe you tied this box with a rope. Then you're pulling this box in this particular direction. So it's either you're pushing the box or you're pulling the box. I don't know how you're doing that, but this could be the force in this particular direction, making the box move in the horizontal direction like this. Now, if the box is going to move in this direction, there will be another force whose job is to stop this box from moving. That force is what is called, shown here as FF, friction force. The friction force always opposes the motion of an object. So whether an object is moving or an object is in motion, there is always friction there to make sure that particular object comes to a stop. If the object is already at rest, the friction is there to make sure that the object stays at rest. If the object is moving, the friction's job is that that particular object should come to a slowdown, to slow down this particular object so that it comes to a stop. So, right now, with this simple box sitting on the floor, as you can see, we can identify 4 types of forces. There are 2 forces acting in the horizontal direction. There's this force. There's also the friction force. The force F, which is pulling the box this particular direction to the right, and the friction force, they are in the horizontal direction. These are the forces we are going to use to work out the resultant force in the x direction. This force, the weight of the box, Fw, and F and the normal force, these are the forces acting in the y direction. These are the forces we are going to use to work out the resultant force in the y direction. So it's very simple to find the resultant force. You just add this force plus this force. Of course, their directions are different. This one is pointing in a different direction. This one is pointing in a different direction. So you need to choose which one is going to be the positive x direction, which one is going to be the negative x direction. Usually, friction is always in the direction opposite the direction in the box is moving. So usually we tend to choose the direction in which the box is moving as the positive direction. So this box, the assumption is that this box is going to move in this direction. So the friction is going to be the opposite direction. So you tend to choose the direction in which the box is moving as the positive direction, or the direction in which the velocity is increasing. Okay. The other type of force which you're going to meet is a force which is in a rope or in a string. For example, the same box which you have here, you can put this box on a floor, and this particular floor is going to generate a normal force. However, you can also tie this box on a string, then hang it from somewhere. When you hang this box from somewhere, this box still has mass. And we are assuming that this box is still on the surface of the earth somewhere, hanging in the air. Because of this mass, this box is going to have weight. The weight of this box is going to point down like this. That's what the weight is going to do. The weight of the box is going to point down like this. However, this weight is supposed to cause the box to move, or the velocity of the box to increase. The velocity of the box, however, in this case will not increase because this box is tied to a rope. So there is this rope supporting the box. In this rope, there is a force called tension in the rope. So what the tension does is basically what Newton's third law of motion says. The tension is usually equal but opposite to the weight of that particular object. Okay? the tension in a rope would try to be equal but opposite. Again, if you increase the mass of this box, if we keep on increasing the mass of the box, it means that we are going to increase the weight of the box. However, this rope will try to generate, out of the material it is made of, it will try to generate a tension which is equal to the weight of the box. If we continue increasing the mass of the box, the weight will increase. At some point, the rope will fail to generate enough force to balance the weight of the box. So when that point reaches, this rope will start breaking and it will cut. That's why things cut. If you've got something which was being supported by something, when the rope cuts, it basically tells you that that particular rope failed to generate a force which is equal to the weight of the box. So if the material of the rope can't generate the force, then a rope tends to cut and you tend to fall. This thing usually happens when, for example, if you have a swing, you're on a swing, then someone heavy sits on that swing. When someone heavy sits on that swing, the end result is really that that swing is going to break. Any questions on tension and weight and how it is related to Newton's third law of motion? Is there a question?
No question.
Okay. Now, our next bit, which is going to be the last discussion we're going to have, focuses on, we're going to look a bit on what the friction force is. Let me just close the door to the house. Mosquitoes. Okay, now, as we have said, the job of friction is to oppose motion. That's what friction does. Friction opposes motion. So when you have something which is moving, the friction between the floor on which this particular object is moving and the object, the friction's job is to reduce the velocity of this object so that this object comes to a stop. So the friction is always opposite the direction in which the object is moving. So the job of friction is to impede or to oppose whatever motion is happening. How do we get the friction? Well, the friction, first of all, before we get the friction, there are two types of frictions. There is friction which an object has when an object is at rest. There is also friction which an object has when an object is moving. The friction which an object has when it is at rest, that is what you call static friction. Static friction is the friction which an object has when it is at rest. The friction which an object has when it's moving, that is what we call kinetic friction. Now, this static friction and kinetic friction, they are related. Okay? Static friction and kinetic friction are related to the normal force. The normal force, remember what the normal force is? The normal force is the reaction of a surface on which a weight has been exerted. So if you have a mass, then you get this mass, you put it on a surface. Whether this mass is moving or not, there is going to be a normal force, because the surface on which you have put this mass, this surface is not going to be happy. So this surface is going to push back against this particular mass. So the pushback force which the surface exerts on the object exerting a weight on it, that is what we call the normal force. So as you can see here, whether the object is moving or the object is not moving, there is going to be a normal force. And friction depends on normal force. The amount of friction which is going to be generated depends on the normal force. So here we have static friction force is equals to the coefficient of friction multiplied by the normal force. So if the normal force is large, then the friction force is going to be large. Are we clear? For starters, if the normal force is large, then the static friction force is going to be large. The normal force depends on the weight. So if the weight of the object is large, then the normal force will be large, which means that the friction force is going to be large. For static friction also depends on something called a coefficient. So whatever the static friction is, when this particular object is at rest, you get your static friction force, then you divide your static friction force by the normal force. When you do this, what you get is something called a coefficient of static friction, or a coefficient of friction. So whatever your friction is, you get your friction, then you divide it by the normal force. What you get is what is called a coefficient of friction. A coefficient of friction is the ratio of the friction force to the normal force. If your object is at rest, so the coefficient of friction you're going to get is what is called the coefficient of static friction. Coefficient of static friction is equal to the static friction force divided by the normal force. So this is mu s. This mu s is the coefficient of static friction. Okay, so if you write this whole thing, you end up with friction force F is equals to the static friction force, coefficient of static friction, multiplied by the normal force. So always, friction force depends on a coefficient multiplied by the normal force. So if the normal force is large, then the friction force is going to be large. This coefficient depends on a number of things. The coefficient will depend on how smooth the surface is on which this particular object is sliding. It also depends on whether there is a lubricant, for example, oil. If there is oil between the particular surface, the object and surface, and it also depends on what these things are made of, what the object is made of, and what the floor is made of. So it depends on a number of things. So out of these things, then you get your coefficient. Engineers have got a way of working out what the coefficient is. So you do that. Okay. So that's how you get your friction, your static friction. Static friction is usually, as you can see here, maximum. So when the friction force is maximum when an object is at rest. That's why we have written here friction force maximum. Friction force max is equal to the coefficient of friction multiplied by the normal force. When an object starts to move, then we start talking about kinetic friction force. So there is also friction present when an object is moving. That friction which it has divided by the normal force which is being exerted on that particular object, then you get yourself something called a coefficient of kinetic friction. So the coefficient of kinetic friction mu k is equal to the friction force the object is experiencing divided by the normal force. You rearrange this whole thing, you end up with kinetic friction force is equal to the coefficient of friction force, or coefficient of kinetic friction multiplied by the normal force. This F is equal to mu k multiplied by Fn. There is a difference between these. This is the friction when an object is moving. The friction force, the coefficient, the kinetic friction force is equal to mu k multiplied by Fn. This equation 13 and this equation 11, there's a small difference there. You can see that here for equation 11 we are saying that the friction force here is maximum. Okay, we are saying that the friction force is maximum. That's what we are saying. The only reason why the friction is going to be maximum, as you can see, we are multiplying mu s, which is a coefficient of static friction, multiplied by Fn. Here we are also multiplying mu k by Fn. The only reason why this is going to be maximum is because this mu s is not the same as mu k. Otherwise, the normal force Fn is the same. Whether an object is moving or an object is at rest, the normal force is the same because the normal force is equal to the weight of that object. If an object is at rest or an object is moving, the weight is the same. So if at one point friction is maximum, the reason why it's maximum is because of this. The coefficient of static friction and the coefficient of kinetic friction are not the same. Usually, the coefficient of static friction is larger than the coefficient of kinetic friction. That's the reason why there is more friction when an object is at rest than when an object starts moving. An example which people could have experienced is when you're trying to push a car. A car is heavier when it has stopped, and it's lighter to push once the car has started moving. The reason is because when the car is at rest, it's this guy. The coefficient of static friction is large. Once the car starts moving, the coefficient changes to this, coefficient of kinetic friction, which is smaller. Are we clear on these type of forces? Especially friction, because friction is always going to be there as long as things are moving. So you cannot ignore it. Even if we tell you, say, there is a frictionless surface, there is no surface like that in the world. We do not have a surface which doesn't have friction. All surfaces have friction. So friction, it will be there. So it's up to you to find out on this particular surface, is this object at rest or it's moving? If it is at rest, then the kind of friction which is present is static friction. How do you find static friction? Ff max is equal to the coefficient of static friction multiplied by the normal force. If the object is moving, then there's kinetic friction. How do you find the kinetic friction? It's the coefficient of kinetic friction times the normal force. We are going to give you the value of mu k and mu s. Usually we tend to give you these. We tell you the coefficient of static friction is this much. The coefficient of kinetic friction is this much. Then we tell you the mass of the object. From the mass of the object, we expect you to get a normal force. As we are going to find out in our next class tomorrow, the normal force usually tends to be equal to the mass of the object, the weight of the object, and we know how to get the weight. The weight of the object is this, mass times g. So we know how to get the weight of the object. The weight of the object is this, mass times g. But tomorrow we are going to show that the normal force, Fn, is always equal to the weight of an object. So this Fn is equal to the weight of the object, which is equal to mg. So we will give you the mass of an object. We expect you to know how to get the weight. From that weight, we expect you to get the normal force. Then with that normal force, with the value of coefficient of friction you have given you, whether it's coefficient of static friction or the coefficient of kinetic friction, we expect you to find the friction force. This friction force will be trying to slow down your object. Are we clear? So we'll stop here tonight. We'll continue tomorrow, where we are going to calculate resultant forces from those two particular diagrams you have seen. Any question? Is there a question? Other people? Do you have questions? Okay, so if you've got no questions, we'll stop here. The recording will be uploaded to YouTube if you want to watch it again. And also, the links will be posted in Moodle this very night. Sorry? The what? Yes.
I'm having a question. You said there's any.
Yes, what's the question? Usually that's what people tend to do. If you use the XY plane, you can use the XY plane as your guide. So whatever force is pointing down, you take it as a negative force. Whatever force is pointing up, you take it as a positive force. So usually that's the simplest thing to do when you take the XY plane as your guide. Any other question? Yes? Is there a question? Okay, if there are no further questions, we'll stop here. We'll continue tomorrow. Alright, so good night. I'll stop sharing my screen. Yeah, and see you tomorrow.